YouTube? It's your boy JOSHABRAHAM. Oh, ho, ho, ho. We're back. Yeah, we're back. Oh, no, don't tell me the mic is muted. Nope. We're back. We're starting the new year. 2026. It's gonna be hella lit. Hella lit. So, I remember last time it was molecular orbitals. I'm having a slight throat issues, but it ain't gonna stop me. It ain't gonna stop me. Dude, the timetables went fucking. Didn't. Now, next day, it's Friday. I missed the. Dude, I missed the whole morning sesh. Okay. But we still got time. Hey Siri, set a timer for 30 minutes. Play, bro. Why is the laptop a bit too slow? Why is it slow? So we got the valence bond, no, molecular orbital theory. Lone pairs, Lewis structure, valence, electron pairing, bond order, molecular orbital, orbital overlap pictures. The coffee tastes so bad. YouTube, just a minute. I'm just gonna mute just for a second. I'm done. I'm done. Dude, it's fucking snowing out here. My next cycling video is gonna be amazing. Ugh. Ah. So F2 is single bond, right? It's SB hybridization. Okay, I'm gonna start today's session with a sentence I believe is right. The F2 is an SB overlap. Please. No. That's it. So involved with the hybridized orbitals. Molecular orbitals. The 2s orbitals are lower in energy than 2p orbitals, so molecular orbitals from 2s are lower in energy. What? Overlap of 2p orbitals is greater than that of 2pxy. Okay, so yeah, okay, I get that. So the energy of the bonding 2p. So bonding sigma 2p is lower than that of anti-bonding 2p is higher than both pi and pi star molecular orbitals are doubly degenerate. Could you explain? To be to be most these are molecular orbitals formed from the 2p atomic orbitals of the two atoms. Each atom has a 3p orbital. Oh shit. These are molecular orbitals formed from 2p atomic orbitals of two atoms. Each atom has 3p orbitals. Okay, sigma and pi molecular orbitals from 2p orbitals. One pair of 2p orbitals, say pz, overlaps head on head to form a sigma 2p bonding and sigma 2p sigma star 2p anti-bonding. The other two 2p orbitals overlap side. So these head on, I'm guessing these two head on overlap is gonna be in the same plane or the same axis of the nucleus of the atoms involved. Thus the sigma bond, while the other twos are having electron density bonding molecular orbitals sigma increasing 2p interaction. What do you mean? Why is pi filled in before no bond order 3? Exactly, let's clarify the step by step sigma 2p bonding, anti-bonding the 2pz orbital head-on along the axis connecting the two nuclei. Electron density is concentrated along this nuclear axis. That's why it's sigma bond. That's what I thought. Molecular orbitals from 2p atomic orbitals, adding 2pz orbitals along the internuclear axis produces a bonding 2p sigma 2p and anti-bonding sigma 2p sigma star 2p orbital. Adding 2px orbitals perpendicular to the internuclear axis produces a bonding pi 2p and anti-bonding pi star 2p. Wait, I gotta see this in person. So that's the negative, that's the positive. If two they connect and form this one, they form, that's the pi bond. Okay, again a pi bond, while 2pz is anti-bonding. They ripple each other. So can I say the if the anti-bonding orbitals fill up, can I say the nuclei of the two atoms starts repelling each other, that the reason for not bonding? But could you also explain how the electrons behave? Anti bonding orbital is filled? How is the anti-bonding orbital being filled? Results in the non-bonding of the atom. Covalent bonding, multiple bonds, non-polar pi bond, polar pi bond. So 2p atomic orbitals. So this is carbon-carbon. So we got pi bonding, pi star. Less electronegative. How anti-bonding orbitals work. A bonding orbital is formed by constructive... Oh yeah, the constructive and destructive interference. The electron density builds up between the two nuclei, which pulls the nuclei together, lowering the energy. The anti-bonding orbital is formed by destructive interference. Here, the wave function of the two atomic orbitals cancel out in the region between the nuclei, creating a node. Along the bond axis, destructive interference, wave functions of the two atomic orbitals cancel each other. Wave functions. So wave functions of the atomic orbital. That's what controls this. Okay, electron behavior in anti-bonding orbitals. Oh fuck. Dude, I can feel the sinus pressure. I need to take some steam. So Simplified MO scheme for CO. Yo, gang, 84 subs. That's crazy. Non-polar pi bond in both atoms are identical. The two p orbitals of carbon have same energy when they overlap sideways to form pi bonds. The bonding pi molecular orbital has electron density equally shared between the two carbons. The wave function is symmetric. No dipole moment. Electron density centered between the nuclei. Pi bond is non-polar. In CO, the atoms are different. Oxygen is more electronegative than carbon. Mhm. 2p oxygen's 2p orbital are lower in energy than carbon's 2p orbital. Why? 6, 8, 2. Mhm. When pi molecular orbitals form, the bonding pi orbital is skewed towards the oxygen. The wave function is symmetric. What are these? Metallic bond, I can't wait to get there. Could you explain more on this? Could you also explain why? $30. God damn it. Okay, so we set a timer for 30 minutes. Okay, it's 30 minutes. I should take that push up. Ah, man. Fuck, you know. Below is the clean, cost effective explanation. No hand waving. Strong, a nucleus attracts the shared electrons in the bond. The tendency to pull an electron comes from two concrete factors. Nuclear charge, carbon 6 protons, oxygen 8 protons. Oxygen's nucleus pull harder than electrons. Pull harder on electrons because it's just more positive charge due to increase in proton number. Shielding, almost the same for carbon and oxygen, both use 2s and 2p valence orbitals. Inner shell, 1s for both. Shielding is nearly identical, so extra plus 2 charge in the oxygen is not cancelled out. Why oxygen's 2p orbital is lower in energy than carbon's? Orbital energy is not arbitrary. It is set by how strongly electron is bound to the nucleus. Compare C to O. Because shielding is similar, oxygen 2p electrons feel larger effective nuclear charge. Let me take a piss. Push-ups. What? Dude, it just stopped working. What the Why oxygen's 2p orbital are lower in energy than carbon? So uh results in positive. Is this only for Okay, we got to the metallic bond. Almost. Valence electrons are only weakly bound. Valence electrons are weakly bound and can therefore be removed easily. Formation of lattice of positively charged metal ions. Metal ion nucleus per core electrons. Total charge of all electrons equal to total charge of all positively charged metal ions. Short answer, both sigma and pi are polarized in CO, not just pi bonds. Polarization is about energy mismatch, not bond type. A bond becomes polar when two atomic orbitals that form in two different form have two different energies. Oxygen's AO atomic orbital are lower in energy than carbon's. Higher electronegativity. This is true for both 2p and 2s derived orbitals. So molecular orbital form is asymmetric. Mm-hmm. Although bonds are sigma and pi bonds are polarized, they're not polarized equally. Sigma bonds have strong overlap, more shared electron density, more polarized. Okay, sigma bonds contribute to the polarization more, while pi bonds Typo moment. One thing students often get wrong. You avoided it. Only pi bonds are polar. Wrong. Sigma bonds are symmetric by definition. Wrong. Okay. I avoided it. Final exam ready statement. In CO, both sigma and pi bonds are polarized towards oxygen because oxygen's atomic orbital are lower in energy than carbon's, causing electron density in all bonding orbitals to be shifted towards the oxygen. So the electron density goes towards the oxygen because oxygen uses less energy, lower in. So here the oxygen having in the electron density shifting could you what is the what term? What's the exact term? No, not exactly. Whatever. Atomic orbitals for molecular orbitals, number of molecular orbitals, number of atomic orbitals, energy difference between molecular orbitals decrease with increasing in number, formation of energy bands overlap partially, bonding and anti-bonding. When filled with electrons, bonding and anti-bonding characters increased. What the Lower energy means oxygen's atomic orbitals lower orbital energy, electrons are more stable. Lower orbital energy. Okay, so orbital energy is what difference in orbital energy is what results in polar covalent bonding, and the one having lower orbital lower orbital what? Lower orbital energy is gonna have more electron density towards itself. Okay. Come on. Below is the clean exam safe explanation for metallic bonding tied to core idea of metallic bonding. Metallic bonding is electrostatic attraction between a lattice of positive metal ions, a C band of delocalized valence electrons. No localized electron pair, no discrete two atom bonds. That's the speciality of metallic bonds. No two atom bonds. Oh. What? Metallic bonding equals electrostatic attraction. That is why electrons form positive ions easily. Low ionization energy. Metal atoms have Loosely held valence electrons that are outer orbital are far from the nucleus, shielded by inner electrons. Electron cloud, electron C model, D-log collect. Cannot be assigned to a single atom, are evenly distributed within the lattice, held by metals by electrostatic attraction. Electrostatic attraction. So the valence electrons are held by, so held in the orbitals due to the atomic orbitals for molecular orbitals. Number of molecular orbitals equals number of atomic orbitals. Energy difference between molecular orbitals decrease with increasing. Yes, that statement is correct. Clarify. Valence electrons in the metals are delocalized and are held by the metal by electrostatic attraction to all the positively charged. I think the electrostatic attraction, I think there was somewhere I saw this. It was the polarized, yeah, covalent bond dipole momentum. These were also electrostatic. If I remember, these were also a form of electrostatic correct, okay. Energy difference between energy bands overlap partially. Energy difference between molecular orbital decrease with increasing number of atoms. Formation of energy bands. Energy bands overlap partially. What is this? Empty molecular orbitals. So, in the case of metallic bond, the anti-bonding orbital is not a thing, at least among same metal elements. Case XC. Stupid. Stupid. Exactly. In metallic bonding, the picture is a bit different from discrete molecular orbitals. Each metal atom contributes to its valence electron to the localized electron C that's spread across the whole lattice. You don't have a distinct bonding versus anti-bonding molecular orbitals like small molecules. Instead, the orbitals from the atoms combine to form bands of energy. A lot to take in. Again, that's a lot to take in for me. You feel me? I am not a very intelligent human being. If I was, I would have passed the exam already. So that's a lot to take in as a below average human being. Bonding, anti-bonding, when filled with electrons, bonding slash anti-bonding character is increased. Oh, metals are deformable, electrically conducting, thermally conducting, showing a metallic luster. I know it's thermally conducting, electrically conducting, showing a metallic luster. What is this? Semiconductors. Dude, it's snowing too much outside. Whew. 30 minutes. Okay, you know what? I don't want to push too much. I'm gonna end the stream. I'm gonna go get a coffee, and we're gonna start with the biochemical kinetics for 1 hour. And before that, I need to send an email to my professor. Okay, 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 okay. Peace out, YouTube.